One of the problems that we encounter with the timeout triggered retransmissions that we looked at is sometimes a timeout period can be too long, and this can cause a long delay before resending a lost packet. So it's a little inefficient. So to get away around that, TCP has the concept of a fast retransmit. And the way the fast retransmit works, um, if a sender receives 3 acknowledgments for the same data, basically 3 duplicate acts, then TCP automatically resends an unacknowledged segment with the smallest segment number. Since it's likely that the unacknowledged segment is lost, we don't wait for a timeout. So we can do this fast transmit quicker than we could do a timeout. We don't want to make the timeout value too short because then we would always be retransmitting packets, and that's extremely inefficient. So this kind of helps us with that balance. So with fast retransmit, the sender can detect lost segments by, like we said, locating duplicate acknowledgments. The sender often sends many segments back to back. If a segment is lost, of course, it receives many back to back. If a segment is lost, there will be likely many duplicate acknowledgments. So let's take a look at a graphical representation that will hopefully help us understand this better. So imagine that our host, which is doing pipelining, sends a total of 5 data packets in one sequence. Again, obviously the first one has 8 bytes of data, the second one has 20 bytes of data. So we're expecting to see sequence for the acknowledgement sequence number 100, and then 120, etc., etc. So in the case of fast retransmit, it sends the first, and it sends the second, and then it sends the third, the fourth, and the fifth. The receiver receives the first, so acknowledges the first, doesn't receive the second, receives the third, re-acknowledges the first, receives the fourth, re-acknowledges the first, etc. So what this ends up looking like from the point of view of the sender is it sees a duplicate acknowledgement because every time host B receives a packet that's out of sequence from the second packet which was lost, it re-acknowledges the last good packet. So TCP is able to use this information to determine, hey, that the packet with that sequence number likely was lost. I'll retransmit, and then of course the host will send an cumulative acknowledgement of all the other packets that it received. Okay, let's talk a little about the concept of flow control. So one of the things we want to make sure is because we want to have reliable data, we don't want to have a situation where a sender will overwhelm the receiver. That'll basically cause too many lost packets, too many retransmissions. You maybe get in this situation where we really can't send the data. So it's important. There's really no need to send the data at a faster rate than the receiver can handle. So we have a mechanism in place that allows the receiver to control the flow of data. So here we have an example where we have an application that it has a socket is communicating with its TCP socket receive buffer. So it can be a situation where maybe the application has a lot of processing and it is removing data from the buffer slower than the receiver is delivering or the sender is sending. So really, you have an application that just can't, for whatever reason, I mean, how it's designed or what it has to do with the data, it's just not getting the data from the buffer fast enough. And this is why the receiver has to have some sort of way to throttle back how fast the data is being received. So we have the concept of TCP flow control. So in TCP flow control, let's consider the following variables. We have the last byte that was read. That's the last byte in the data stream from the buffer, read from the buffer by the application host, application process in host B. So this is basically the point where the application is left off. It hasn't read any more bytes than this particular byte in the buffer. Then you have the last byte received. That is the number of the last byte in the data stream that is derived from the network and placed in the received buffer. So obviously the difference between these two, last byte read and last byte received, is basically the contents of the received buffer. So because TCP is not permitted to overflow the buffer, remember this is reliable data transfer, the difference between these two, the last byte received minus the last byte read, okay, so that's the accumulation of everything received by the buffer minus what was read by the application, has to be less than or equal to the received buffer. If that's not the case, then we're going to lose data, which is not acceptable. The receive window, which is denoted by RWND, is set to the amount of spare room in the buffer. So it basically is the size of the buffer minus the what has been received minus what the application has been able to read. So host A, therefore, needs to keep track of two variables. The last byte, host A being the sender, keeps track of the last byte that it sent and the last byte that was acknowledged. The last byte sent minus the last byte acknowledged is the amount of unacknowledged data that A has sent into the connection. By keeping the amount of unacknowledged data less than the value of RWND, which is the value that the receiver sends back to the sender, host A is assured that it's not overflowing the received buffer at host B. And this is because data is not acknowledged until it's actually sent to the application. So anything unacknowledged could be something sitting inside that buffer. So to make this work, host A ensures that the last byte sent minus the last byte acknowledged is less than or equal to RWND. So basically, in order for this to happen, the receiver advertises free buffer space by including the RWND value in the TCP header of receiver to sender segments. So here we have, on the receiver side, it's receiving TCP segments, it's going to the application process for the socket, and you have the received buffer, and the received buffer has free buffer space, okay, space is left over for more TCP segments, and buffered data that the application has not yet read. The difference, or basically the free buffer space, is also this RWND value. So this RWND value is sent back to the sender. Now the receive buffer, we've actually already took a look at this when we did that socket programming, is set via socket options, and the typical default value is 4096 bytes. And many operating systems do try to control the receive buffer on its own, make adjustments depending on, and it keeps track of the data flow. Sending limits. The sender limits the amount of unacknowledged in-flight data to the receiver's RWND value. So basically, the sender tries to not send more packets than can fit in this free buffer space. And this guarantees the receive buffer will not overflow.